Hi guys, so the next question is about rings. And what do we need when we talked about rings? We just need their radius, right? So if this is the first ring, let's note here with I, the round numbers, and what radius that the rings have. The rings have a radius which we're gonna call R1, and each ring have the charge density lambda 1. And let's do another ring. The other ring, we're gonna change this one to this one. So the other one is on the same axis, which means on top of each other. So we have here another ring. Let's do it bigger, which have the radius R2, the charge density lambda 2, and let's call it ring 2. This is ring 1, this is ring 2, perfect, this is good. And let's denote this point 1 and this point 2, perfect. And the question is, what is the potential in location 1, okay, due to ring 2? Okay, what do I mean is, what is the potential phi in point 1 due to ring 2? That's the question. Okay, so we know from the lecture what is the equation for potential due to a ring, right? What is the equation was? It was the charge, right? The charge in the ring multiplied by k divided by the square root of the radius of the ring plus z, which is the height above the ring. Let's do this as z-axis, okay? And both of them squared, right? Perfect. In our case, Q is not given, but we have the charge density. And what are the units of charge density? Is Coulomb charge per meter. So if you're gonna multiply this by the length of this circle, we're gonna get Q. So to calculate it, let's use the red pen. Let's use the red pen. So it's equal to, first of all, I'm gonna take care of Q. So what is the charge on this? We are looking for what is the potential in this dot. So what is the charge from this ring, number 2, is lambda 2 multiplied by this length, which is a circle, so I know it's 2 pi r2. Perfect. And here, square root, I know, sorry for the r here. And this is a general term. Let's do it like this. This is phi general. And if I'm looking for phi 2.1, it's this equation when I substitute all the different parameters. Okay, perfect. And what is the radius? The radius is radius 2 square plus, let's call this height, which is given h. So this is h square. And I forgot here to put k. Yeah, k. So that's it. We found phi 2. Phi 2 on 1. And the next question I want to ask you, what is actually the potential in 1 due to this ring, the first one? So the next question is, what is phi? What is the potential in point 1 due to, right, to ring number 1? So this is again the same equation. It's qk over r squared plus z squared, right? And let's put what we already know. We know Q, right? Q is right now this charge, all the charge over here, which is 2 pi r1 multiplied by lambda 1 multiplied by k, right? Multiplied by k divided by the radius of this one, which is r1 squared, plus, let's do it more comfortable way, r1 squared plus the height from the ring. And what is the height between this point and the ring? Actually it's 0 square, even I would say, okay? To understand where it's coming from. And this is equal to what? So this r square and this are gonna cancel out. We're gonna have 2 pi lambda 1 k, and that's it, actually. It's not a ring, it's just a solution. So we found what is the potential at point 1 due to this ring and due to this ring. So what's gonna be the next question? The next question is gonna be what is the total potential in point 1 due to everything we got in the wall. So let's make it clear. We're gonna clean this stuff up. Let's clean this, we don't need this anymore. This one we need that. This one we don't need, maybe only the result. So we know that the potential, here it is, let's do it in blue. The potential phi of ring 1 in point 1 is equal to 2 pi lambda 1 k. Okay, so we found these two. And the next question is, the third question is, what is the potential at this point? So what is the total potential at point 1? So we can use the superposition. We know that the superposition concept working on electrical field, on forces, and if it's working on electrical fields, in particular it's going to work on potential, because potential is based on electrical field. It's a summation of electrical fields, right? In the direction, right? So what is this equal to? It's equal to the first one, phi. Let's do general. It's equal to the sum of all the objects in the world that apply some potential on point 1. In our specific case is this one and this one, which is 2 pi lambda 1 multiplied by k plus the second term, which is this lambda 2 pi r2 divided by square root of the radius r2 square plus 8 square. So this is the solution for that. Perfect. So we did this one also. We found what is the potential. So the first question was, what is the potential due to ring? This was the first question. What was the ring due? What was the potential at point 1 due to the big ring, right? Ring number 2. That was the first question. The second question was, what is the potential in point 1 due to the ring 1, which is kind of a height 0, as we said. And the third question was, what is the total potential in point 1, which was the contribution of the two rings. Okay, good. So now we're gonna proceed on, and now it's given what is the potential. This was phi 1. What is potential phi 2? It is given, and the term is really similar to this one. Why? Because we just change the players. We change this ring with this ring. So the solution is, I'm gonna give it here. So it's given. This is the fourth question. So fourth question. This is 4. And what is this given? This is given. Phi 2 is given. Phi 2 equal to 2 pi k lambda 2 plus lambda 1 multiplied by r1 square root of r1 square plus h square. Perfect. This is given. And if you look at this is pretty similar to what we did. So if you want to practice and see it for yourself, you can see that this is actually the same one, but opposite in direction and opposite with the r. This is r1 and not r2, because right now I just changed the point that I observed. And the question is, how much energy do I need to take the charge Q from point 2 to point 1. This is the question. So what I need to do, I need to take some charge from point 2. Here there's some charge. Let's put here Q. How much energy it's going to cost me to take this one and pull it up here, up until I get to point 1. And I want to remind you a little thing from physics 1. In physics 1 you learned potential energy, right? Which was that E, right, equal to mg delta H, actually, right? The change in the height. If I want to take something from the floor and took it up high, right? So I need to multiply by the change in the height. And something really similar happened in electrical field. If I want to calculate the potential U, the work that I've been doing, U, so I'm gonna multiply it by Q, which what we said was Q. Q is actually it's similar to what? To the mass from physics 1, right? We talked about charge, not about masses. And here we're gonna put the potential, the change in the potential, phi2 minus phi1. Okay, you see the similarity? So what is a little bit different? So in physics 1, G was always constant, remember? It was minus 2.8 meter per second square, right? And in electromagnetism, here it's actually, in our class, it's E, right? Let's do it in a more clear way. Let's delete this one. EMGH, E equal mgh, and here we don't use E because we don't want to confuse with electrical field, but here it's Q E, let's do delta H, and here it's delta R, the distance. So this is kind of similar equation. The thing is that electrical field change all the time in this class. And compared to physics 1, G never change most of the time, it depends what you do. If you're working on stars, on the moon, stuff like that, many changing really dramatically in the height, yes, G can change. But usually it did not change so much, so you always took it as a constant. But here you have electrical field. The electric field can change from here to here. We're going to see it in the next question. So that's the idea. And this term we called it the potential. And the proper way to say it is, as you saw in the lecture, it's actually the integral, right? It was the integral way. We're gonna talk about it in the next question, but I just want to give you a head up. So if I want to know what is the energy, so the work I need to do, the energy, the potential energy, is actually Q, the charge that I want to transfer, multiplied by the change in the potential, which is equal to Q phi2 minus phi1. And we just get phi2 in this question as given, and from the previous question we have phi1, so we actually have the two potentials, and if we subtract them from each other, we're gonna get this term. This is equal to, we're gonna get 2 pi k q, and this outside of lambda 2 minus lambda 1 plus lambda 1 R1 divided square of R1 square plus H square plus H square minus lambda 2 R2 divided by square root of R2 square plus H square. So this is the idea. Let's close it. Okay, so this is the result. And what I want you to notice here is that you can look at the different cases. Let's delete this one. So I want you to see that this is the energy, right? The work that I need to do. Potential energy, usually you put it in that way, but it depends on the question, depends on how you used to stuff, but this is okay to put it both, but most of the time you're gonna see this term in class. And I want to talk to you what's happened if U is equal to 0. For example, if the two rings are the same, for example, they have the same R, R1 is equal to R2, lambda 1 equal to lambda 2. So what we're gonna have here, and actually, yes, what's it gonna have here? We're gonna see that this equal to 2, which means it does not care. It doesn't care if to move to that place, to move from 2 to 1, 1 to 2, it's not gonna do it by himself. If U was positive, it actually was stuck, for example, at point 2, and you need to apply a lot of energy, this amount of energy, to take it from here, rip it off, and put it in 1. That's the idea of positive energy, okay? And negative energy, if it was smaller than 0, it actually won't to go there. And if I would not stop it, it's gonna happen. If I would not put some positive energy to balance it, to take it to 0, it's gonna happen. For example, here the work, right now this pen have a positive energy, right? Is above the floor. If I'm gonna lift, I will stop putting force of lifting this heavy stuff, it's just gonna fall on the floor. So the same thing happened in electrical field. So this Q is actually affected by some electrical field, and we can see it by the potentials. So there's some potential that won't take it to this location, and we can see what is actually the energy that you have, what is the height, different in heights like in physics 1, by this term, which we see a big dependency on the radius, on the amount of charge, on the height between them, so how far away the rings from each other. So this is the general idea. And now let's move to the next question.